Let's finally demystify Hamiltonians and diagonalization. George, I want to start with a confession. I have been building this cold atom black hole simulator for months. I can run the code, I can read the plots, I can tell you the R ratio went from Poisson to GOE. But if you stopped me on the street and asked, what actually is the Hamiltonian, how do you build it, and what do you literally mean when you say you diagonalize it, I would fumble every one of those three.
That is a wonderful confession, and honestly, it is the most common one in this whole field. People operate the machinery fluently for years while the foundations stay a little foggy. So here is my promise for the next hour. By the end, you will be able to answer those exact three questions: how the Hamiltonian is constructed, how it is solved, and what diagonalizing means. And you will be able to answer them using your own Hamiltonian, the one sitting in your QSM core.py file. No toy from a textbook, your actual chain.
That is exactly what I want. Ground it in my project, or it won't stick.
Deal. And I want to warn you up front, I am not going to shy away from the math. But every piece of math I write, I will speak in plain words, and I will attach it to something concrete you can picture. If at any point a symbol floats free with no anchor, you stop me.
I will absolutely stop you. Okay, start at the very bottom. What is a Hamiltonian? And please don't say it's the energy operator and move on, because that sentence has never once helped me.
Fair. Let me earn that sentence instead of just asserting it. Forget quantum mechanics for a second. In ordinary classical physics, the Hamiltonian is a formula for the total energy of a system in terms of its configuration. A ball on a spring, the energy is 1/2 mva squared plus 1/2 kx squared. Kinetic plus potential. Give me the position and velocity, I hand you back a number, the energy. That's it. The Hamiltonian is the accountant that converts "here is the state of the system" into "here is how much energy that costs."
Okay, energy accountant, that I can hold.
Now, quantum mechanics changes one thing about that picture, but it is a big thing. In quantum mechanics, the state of the system is no longer a point, a definite position and velocity. The state is a vector. It lives in a big abstract vector space. And because the state is a vector, the thing that acts on it, the energy accountant, can no longer be just a formula that spits out a number. It has to be an object that takes a vector in and gives a vector out. An object that acts on vectors is a matrix, so the Hamiltonian becomes a matrix.
Wait, let me slow that down because that is exactly one of my fog points. The state is a vector, a list of numbers. Fine. And the Hamiltonian is a matrix, a grid of numbers. And the matrix acts on the vector, meaning matrix times vector gives another vector. But then where does the energy, the actual number, come from? The whole point was supposed to be energy.
That is precisely the right question, and it is the hinge of the entire subject. Here is the answer. For most vectors you feed in, the Hamiltonian matrix takes them in and gives back some totally different vector, pointing in a new direction. But there exist special vectors, special states, where the Hamiltonian acts on them and gives back the same vector, just scaled by a number. Written in symbols, H acting on psi equals E times psi. The matrix H hits the state psi, and out comes E times psi, the same psi stretched by the number E.
So the matrix doesn't rotate that particular vector into a new direction, it just lengthens or shortens it.
Exactly. And when that happens, when a vector survives the matrix unchanged in direction, we call that vector an eigenvector, and we call the scaling number E its eigenvalue. Those two German-rooted words just mean the special direction and its special number. And here is the physics payoff. For the Hamiltonian, that special number E is an allowed energy of the system, and that special vector psi is the state that has that definite energy. So your foggy sentence, the Hamiltonian is the energy operator, now unpacks to something real. The Hamiltonian is the matrix whose eigenvalues are the allowed energies, and whose eigenvectors are the states that own those energies.
Okay, that landed. Eigenvalues equal allowed energies. Eigenvectors equal the states with definite energy. Let me test myself. So a generic state, some arbitrary vector, does not have a definite energy.
Correct, and that is a deep point you just walked into. A generic state is a mixture, a superposition, of several eigenvectors, and so it does not have one single energy. It has a spread of possible energies. Only the eigenvectors have a single sharp energy. That is why they are also called stationary states, and I want to flag that name because we will need it in about 40 minutes when we talk about time evolution. Stationary means if the system is sitting in an eigenstate, it just sits there, energy fixed, nothing sloshing around. Hold that word.
Stationary states, filed. Now, you said the Hamiltonian is a matrix, but a matrix has a size, rows and columns. What determines how big my Hamiltonian matrix is? Because I have a vague memory that this number is enormous, and it's the reason we need a quantum computer at all, but I couldn't tell you why.
Beautiful. That is the perfect bridge into part 2, which is how we actually construct yours. And the size of the matrix is the whole ball game. But before I can tell you the size, I have to tell you what the vectors are, because the matrix acts on vectors, and the size of the matrix is just the number of components those vectors have. So, what is the state space of your system? Let's build it from the physics up.
Please, because in my head, the state of the system is a fuzzy cloud, and I want it to be a concrete list.
Then let's make it a concrete list. Your system, physically, is a chain of sites. Think of a row of little wells, an optical lattice, sitting in a line. Site 0, Site 1, Site 2, and so on, up to Site L-1, where L is the number of sites. And you drop particles into these wells. In your case, the particles are hardcore bosons, atoms that hop between neighboring wells but refuse to share a well. Two of them can never sit in the same site. That no-sharing rule is the hardcore part, and it will matter enormously in a minute.
Right, hardcore bosons. And I run them at half filling. That phrase is all over my code. What does half filling buy me, concretely?
Half filling means the number of particles n is exactly half the number of sites L. 10 sites, 5 particles. 14 sites, 7 particles. And the reason you fix the particle number at all, half or otherwise, is subtle and worth a second. The Hamiltonian in your problem conserves particle number. The hopping moves a particle from one site to a neighbor. It never creates or destroys particles. So if you start with 7 particles, you stay with 7 forever. That means the giant state space splits into independent sectors. One for 0 particles, one for 1 particle, one for 2, and so on. And they never talk to each other. You only ever have to work inside one sector, the one with your n particles. That is a massive simplification, and it is why every function in your code takes n part as an argument.
Okay, so the matrix is block diagonal by particle number, and I just live in one block. Good. So now, the vectors inside that block, what are they as a literal list?
Here is the literal list. A basis state, one of the building block vectors, is just a specific arrangement of your n particles across the L sites. Particle here, here, and here, empty everywhere else. Because 2 particles can never share a site, each arrangement is just a choice of which sites are occupied. So a basis state is a string of zeros and ones. 1 means a particle sits here, 0 means empty. That is called the occupation basis, or the Fock basis, and that word Fock is exactly the Fock basis function in your QSIM core.
Oh, so Fock basis is literally enumerating every way to place the particles. Let me look at what it does. It calls combinations of range n sites, taken in part at a time, and for each one, it sets some bits in an integer. So it is building every bit string with exactly n ones.
You just read your own code correctly, which is the whole point of this episode. Every occupation string with exactly n ones among L sites is one basis vector. And now I can answer your size question. How many such strings are there? It is the number of ways to choose which n of the L sites are occupied. That count is written L choose n, and spoken it is exactly that. L choose n. It's the binomial coefficient. For L sites and n particles, the dimension of your Hamiltonian matrix, the number of rows, the number of columns, is L choose n.
I'll choose N. Let me get a feel for that number. Small case, 4 sites, 2 particles. 4 choose 2.
4 choose 2 is 6. There are 6 ways to place 2 particles on 4 sites. And I love that you picked that one, because 4 sites 2 particles is going to be our worked example, the actual 6 by 6 matrix we build by hand. But before we build it, let me make you feel why this number is the villain of the whole story. Let's grow L at half filling and watch. 4 sites, 2 particles, 6. 10 sites, 5 particles, 10 choose 5 is 252. 14 sites, 7 particles, that's your Sim 10 default. 14 choose 7 is 3432. 20 sites, 10 particles. 20 choose 10 is 184,756.
It's going from 14 sites to 20 sites. The matrix went from 3,000 rows to 184,000 rows. That's not a gentle climb.
It is a cliff, and it keeps getting steeper. That growth is roughly exponential in L. Every 2 sites you add at half filling multiplies the dimension by about 4. And a matrix's memory cost grows as the square of its dimension, because it's dimension by dimension entries. So that L equals 20 matrix, if you tried to store it densely, is 184,000 squared entries, about 34 billion numbers. At 8 bytes each, that's on the order of a couple hundred gigabytes for one matrix. That is your classical wall, and it is exactly why panel D of your Sim 10 figure exists, and why the project targets quantum hardware around L equals 20. But I'm getting ahead. Let me put a pin in the wall. We'll come back to it properly in part 5. First, let's actually build the matrix for 4 sites, 2 particles, so you can see what lives in those rows and columns.
Yes, I need to see one real matrix, entry by entry, or none of this is real to me. 4 sites, 2 particles, 6 by 6. Go.
Let's set it up carefully because the payoff is worth the care. 4 sites, label them 0, 1, 2, 3 in a line. 2 particles, the 6 basis states. I'll name each by which 2 sites are occupied. State 1, sites 0 and 1 occupied. State 2, 0 and 2. State 3, 0 and 3. State 4, 1 and 2. State 5, 1 and 3. State 6, 2 and 3. That's all 6 ways. Write them down in that order, because the order defines the rows and columns of our matrix.
Got it. Let me repeat them so they're fixed. 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3. 6 states, and that ordering is now law.
That ordering is law. Now your Hamiltonian has 2 pieces, and I want to build them separately because they play totally different roles in the matrix. Let me write the full Hamiltonian in words first. H equals the sum over bonds of kappa sub j times the quantity x sub j plus 1 plus y sub j plus 1 all over 2, that's the hopping, plus v times the sum over bonds of n sub j times n sub j plus 1. That's the interaction. 2 terms, the hopping term with the kappas and the interaction term with the v. Let's take them one at a time, and let's do the interaction first because it's easier.
Why is the interaction easier?
Because the interaction term is diagonal. It never moves any particle. Look at what it says. V times n sub j times n sub j plus 1, summed over neighboring pairs. The symbol n sub j is the number operator on site j. It just asks, is site j occupied? And answers 1 for yes, 0 for no. So n sub j times n sub j plus 1 asks, are both site j and its right neighbor occupied? It's 1 only when there's a particle on both ends of that bond, 0 otherwise. Sum that over all bonds and multiply by v, and you get v times the number of occupied adjacent pairs. It's an energy penalty, or reward, for particles sitting next to each other.
So the interaction just counts how many pairs of neighbours are both filled and charges v per pair. And it's diagonal because counting occupied neighbours doesn't move anybody. You look at a configuration and read off a number.
Exactly. And that read off a number without changing the configuration is the definition of a diagonal matrix element. It maps each basis state to a multiple of itself. State 1 goes to v something times state 1, never to a different state. So let's compute the diagonal for all 6. State 1, sites 0 and 1. Are they adjacent? 0 and 1 are neighbors. That's a filled bond. So one occupied pair. Diagonal energy, V, state 2, sites 0 and 2. Neighbors? No, there's a gap at site 1. 0 occupied pairs. Diagonal, 0. State 3, 0 and 3. Far apart, not adjacent. Diagonal, 0. State 4, 1 and 2. Adjacent. Diagonal V. State 5, 1 and 3. Not adjacent. 0. State 6, 2 and 3. Adjacent. V.
Let me collect that. Down the diagonal, in our state order, the interaction gives V0, 0, V0, V. So states 1, 4 and 6 each pay V because their two particles are touching, and states 2, 3, 5 pay nothing because their particles are separated.
Perfect. You just built the entire diagonal of the Hamiltonian, and it is nothing more mysterious than count the touching pairs times V. Now the harder, more interesting piece, the hopping. This is where the kappas live, and this is where the off-diagonal entries come from.
And this is the part I really don't have a picture for, the XX plus YY over 2 thing. Why does that combination mean a particle hops?
Let me demystify it because it looks like abstract spin nonsense, and it is actually the most physical thing in the whole Hamiltonian. First, the dictionary, hardcore bosons on a chain are mathematically identical to spins 1/2 on a chain. Site occupied is spin down, site empty is spin up. Or the reverse doesn't matter. So each site carries a little spin, and X, Y, Z are the Pauli matrices acting on that site's spin. Now there's a standard fact. The combination X sub J plus 1 plus Y sub J plus 1 all over 2 is exactly the operator that takes an excitation on one site and moves it to the neighbor. In the boson language, it annihilates a particle on site J plus 1 and creates one on site J plus the reverse. It hops a particle across the bond.
So that specific combination is engineered so that when it hits a configuration, it slides one particle one step to an empty neighbor.
Precisely. And crucially, it can only slide a particle into an empty site because of the hardcore rule. If the neighbor is already occupied, there's nowhere to go, and the term gives 0. So the hopping term takes a basis state, finds a particle with an empty neighbor across a bond, and produces a new basis state where that particle has moved one step. It maps one basis vector to a different basis vector. And that, mapping a state to a different state, is exactly what an off-diagonal matrix element is.
So diagonal equals stay put, just count energy. Off-diagonal equals turn into a different configuration. The interaction stays put. The hopping moves you.
You've got the deep structure of the entire matrix in one sentence. Let me now actually compute the off-diagonal entries for our 6 states. The rule from the hopping term, for each basis state, look at each bond. If one end of the bond is occupied and the other is empty, you can hop that particle across, producing another basis state, and the matrix element connecting those two states is kappa for that bond. Let me name the bond couplings. Kappa A for the bond between sites 0 and 1. Kappa B for the bond between sites 1 and 2. Kappa C for the bond between sites 2 and 3. 3 bonds, 3 couplings.
3 bonds, 3 kappas, A, B, C, left to right. Okay, walk me through one state completely so I see the procedure.
Let's take state 2, sites 0 and 2 occupied, because it's the busiest one. Bond A, between sites 0 and 1, site 0 is occupied, site 1 is empty, so the particle on 0 can hop right to 1. What state does that produce? Particles now on sites 1 and 2. That's state 4. So state 2 connects to state 4, with matrix element kappa A. Next, bond B, between sites 1 and 2. Site 1 empty, site 2 occupied. The particle on 2 can hop left to 1, giving particles on 0 and 1, which is state 1. So state 2 connects to state 1 with kappa B. Finally, bond C between sites 2 and 3. Site 2 occupied, site 3 empty. The particle on 2 hops right to 3, giving 0 and 3 occupied, which is state 3. So state 2 connects to state 3 with kappa C.
So from state 2 alone, I get 3 off-diagonal links. To state 4 with kappa A, to state 1 with kappa B, to state 3 with kappa C. That one configuration is a little hub.
It's the busiest hub because its two particles are far apart, so both have room to move in multiple directions. Now compare state 1, sites 0 and 1, particles jammed together at the left end. Bond A is between two occupied sites, so no hop there. Bond B, site 1 occupied, site 2 empty. The particle on 1 hops to 2, giving 0 and 2, which is state 2. That's the only move. Bond C, both sites empty, no hop. So state 1 connects only to state 2 with kappa B, one single link.
That makes intuitive sense. The crammed configuration has fewer places to go. Let me try to finish the rest myself and you correct me. State 3, sites 0 and 3, particles at the two far ends. Bond A, 0 occupied, 1 empty, hop to give 1 and 3, state 5 with kappa A. Bond B, both empty, nothing. Bond C, 3 occupied, 2 empty, hop to give 0 and 2, state 2 with kappa C. So state 3 links to state 5 via kappa A and to state 2 via kappa C.
Flawless. Keep going.
State 4, sites 1 and 2, particles in the middle touching. Bond A, 1 occupied, 0 empty, hop to give 0 and 2, state 2, kappa A. Bond B, both occupied, nothing. Bond C, 2 occupied, 3 empty, hop to give 1 and 3, state 5, kappa C. So state 4 links to state 2 via kappa A and state 5 via kappa C.
Perfect. 2 more.
State 5, sites 1 and 3. Bond A, 1 occupied, 0 empty, hop to 0 and 3, state 3, kappa A. Bond B, 1 occupied, 2 empty, hop to 2 and 3, state 6, kappa B. Bond C, 3 occupied, 2 empty, hop to 1 and 2, state 4, kappa C. So state 5 is also a busy hub. To state 3 via kappa A, state 6 via kappa B, state 4 via kappa C, and state 6, sites 2 and 3, jammed at the right end. Bond B, 2 occupied, 1 empty, hop to 1 and 3, state 5, kappa B. That's the only move. State 6 links only to state 5 via kappa B.
You just constructed by hand every single matrix element of your Hamiltonian for 4 sites, 2 particles. Let me read the whole 6x6 matrix back to you so you can see the object entire. Rows and columns both ordered as our 6 states, 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3.
Read it slowly. I want to hold the whole grid.
1, state 0, 1, on the diagonal, V, and 1 off diagonal, kappa B, in the column for state 0, 2. Everything else in that row is 0. Row 2, state 0, 2. Diagonal is 0. Off diagonals are kappa B, back to state 0, 1, kappa C to state 0, 3, and kappa A to state 1, 2. Row 3, state 0, 3. Diagonal 0, off diagonals kappa C to state 0, 2, and kappa A to state 1, 3. Row 4, state 1, 2. Diagonal V, off diagonals kappa A to state 0, 2, and kappa C to state 1, 3. Row 5, state 1, 3. Diagonal 0, off diagonals kappa A to state 0, 3, kappa C to state 1, 2, and kappa B to state 2, 3. Row 6, state 2, 3, diagonal Vi, 1 off diagonal kappa B to state 1, 3.
And it's symmetric. The entry linking state 2 to state 4 is kappa A, and so is the entry linking state 4 to state 2. Mirror image across the diagonal.
Symmetric, and that is not an accident, it's required. The Hamiltonian must be Hermitian, which for a real matrix like this just means symmetric, and physically it's what guarantees the eigenvalues, the energies, come out as real numbers rather than complex ones. Energy has to be real. In your code, that's the line H equals 1/2 times H plus H transpose at the end of hardcore H. It symmetrizes the matrix to kill any tiny asymmetry. And notice one more thing about this matrix. Because it's the seed of part 5, it is mostly zeros. 6x6 is 36 entries, and we filled in only the diagonal plus about 10 off-diagonal slots. Most of the grid is empty.
Why is it so empty? Just because the chain is small?
No, it stays sparse at every size, and this is important. Any given configuration can only hop into a handful of others. At most, one move per bond, so at most L-1 neighbors in the whole gigantic space. So each row, no matter how enormous the matrix, has only a couple dozen non-zero entries. A matrix that's almost all zeros is called sparse, and that sparsity is the loophole that lets us push past the classical wall. Pin that too. It's the hero of part 5.
Okay, 2 pins for part 5, the wall, and sparsity as the loophole. But first, I really want part 4, because we've built this matrix and I still haven't heard what it means to diagonalize it. I've been saying the word for months, cash it out.
Let's cash it out properly, and I want to build it in 2 layers. First, the pure linear algebra meaning, then the physics reason it's the single most useful thing you can do to a Hamiltonian. Linear algebra first. Our 6x6 matrix, written in the occupation basis, is full of off-diagonal kappas. Those off-diagonal entries are the matrix saying, these configurations talk to each other, they mix. Diagonalizing means finding a new set of basis vectors, a new coordinate system for the same space, in which the matrix has zeros everywhere off the diagonal. Only the diagonal survives, and the numbers left sitting on that diagonal are exactly the eigenvalues, the energies.
So diagonalization is a change of coordinates that makes the mixing disappear.
That's it, said perfectly. In the occupation basis, the natural particle on site coordinates, the states are all tangled. Configuration 2 bleeds into 1 and 3 and 4 through the kappas. But there's a special rotated frame, the energy eigenbasis, where everything untangles. Each new basis vector is an eigenvector, a specific weighted combination of the original occupation states, and in that frame the Hamiltonian doesn't mix anything. It just multiplies each eigenvector by its own energy. The matrix becomes a simple list of numbers down the diagonal.
And concretely, the machinery of that is, what? A matrix U, whose columns are the eigenvectors.
Exactly, and let me make it precise, because you'll see it in your code. Diagonalization produces 2 things. A set of eigenvalues, E1, E2, and so on, the energies, and a matrix U, whose columns are the corresponding eigenvectors, and they satisfy the relation. U dagger times H times U equals a diagonal matrix of the energies. In words, if you sandwich your Hamiltonian between U dagger on the left and U on the right, that's the change of basis. You get a matrix that's zero everywhere except the energies down the diagonal. U is the rotation from the occupation basis into the energy basis. Its columns literally tell you eigenstate number 3 is this much of configuration 1 plus this much of configuration 2 and so on.
Okay, the linear algebra, I follow. Now, the physics. Why is this the most useful thing I can do? Because right now it sounds like a lot of work to turn a matrix into a list of numbers.
Here's why it's the crown jewel, and it comes down to time. The whole point of a Hamiltonian in quantum mechanics isn't just to list energies, it's to tell you how the system evolves in time. The law of motion is the Schrödinger equation, and its solution says, to evolve a state forward by time t, you apply the operator e to the minus iht to it. That's the time evolution operator, e to the minus I times h times t.
And there's my next fog bank. E to the minus iht. H is a matrix. How do you exponentiate a matrix? What does that even mean?
Great, this is exactly where diagonalization earns its keep. So let me answer it head on. Exponentiating a matrix is genuinely a hard, ugly operation. If the matrix has all those off-diagonal terms, you'd have to sum an infinite series of matrix powers, h times h times h, forever. But if the matrix is diagonal, just numbers down the diagonal, then exponentiating it is trivial. You simply exponentiate each diagonal number by itself. E to the minus iht of a diagonal matrix is just e to the minus ie1t, e to the minus ie2t, and so on, down the diagonal. The hard matrix operation collapses into a handful of ordinary scalar exponentials, each one just a complex number of magnitude 1, a phase.
So that's the trick. Once you're in the energy basis, time evolution isn't a scary matrix exponential, it's just multiply each eigenstate by its own little phase.
That is the entire reason diagonalization is the master key. Let me say it as a recipe, because this recipe is literally the evolve state function in your run E05 code. Step 1. Take your starting state and express it in the energy basis. That's the line C0 equals U dagger times ESI0, projecting your state onto each eigenvector to get coefficients. Step 2. Evolve each coefficient by multiplying it by e to the minus IENT. Each eigenstate just spins its phase at a rate set by its own energy. Step 3. Rotate back to the occupation basis to see where the particles are. That's U times the phased coefficients. Diagonalize once, and after that, evolving to any time is just multiplying by phases. No matrix exponential ever again.
Let me make sure I feel why the phases are the answer and not something more complicated. An eigenstate is a stationary state. You told me to hold that word. So under time evolution, it doesn't change its physical configuration, it just rotates its phase.
You just closed the loop beautifully. Yes, a stationary state stays itself. The only thing time does to it is wind a phase, e to the minus IET, like a clock hand going around at a speed proportional to its energy. The probabilities of finding particles anywhere don't change at all. That's why it's called stationary. And a generic state, which is a superposition of many eigenstates, evolves in a complicated sloshing way, precisely because each of its eigenstate components spins its phase at a different rate. The different clock hands drift out of step, and their interference is the dynamics. All the richness of the time evolution, the scrambling, the butterfly effect, everything in your OTOC plots, is just many phases beating against each other. But you can only see it that cleanly once you've diagonalized.
That's genuinely one of those oh moments. The dynamics is complicated because the energies are different, and diagonalizing is what exposes the energies. Okay, so now I'm sold on why we diagonalize. Part 5, how. How does the computer actually do this, and where's the wall?
Let's do it. And there are really two regimes, and your project lives right at the boundary between them, which is what makes it interesting. Regime 1, small enough that you can just brute force it. That's called dense exact diagonalization, and in your code it's the numpy call, either emp.linealg.a, which gives you eigenvalues and eigenvectors, or emp.linealg.eigvalch, which gives you just the eigenvalues when that's all you need.
The H in A, that's for Hermitian.
Exactly, A is the Hermitian eigensolver. It's told the matrix is Hermitian, symmetric, real energies, so it uses a faster, more stable algorithm than the general one, and it guarantees real eigenvalues. Under the hood, it does a very classic thing. It applies a sequence of rotations that gradually zero out the off-diagonal entries, chipping away until only the diagonal survives. That's the literal mechanical act of diagonalization, a computer rotating the matrix into its eigenbasis. For your 6x6, it's instant. For a few thousand by a few thousand, your L equals 14, dimension 3432, it's a fraction of a second to a couple seconds, which is exactly the ED wall times printed in your Sim10 output.
And dense means it stores every single entry, including all the zeros.
That's the defining feature, and it's the killer. Dense storage holds the full dimension by dimension grid in memory, all 34 billion entries at L equals 20, zeros included. The cost has two parts, and both are brutal. Memory grows as dimension squared, and the compute time to diagonalize grows as dimension cubed. So let's watch the wall arrive. L equals 14, dimension 3000, matrix is about 90 megabytes dense, diagonalizes in a second or two. L equals 16, dimension 12,870. Matrix is a gigabyte and change, diagonalizing takes real seconds to minutes. That's your L equals 16 wall probe in run E05, the one you had to drop to 4 disorder realizations for, because it's expensive. L equals 18, dimension 48,000, tens of gigabytes for one matrix. L equals 20, dimension 184,000, hundreds of gigabytes. You physically cannot hold it in a laptop's memory, let alone diagonalize it.
And that's the exact number in my head. The wall around L equals 20. So panel D of Sim 10, the log scale plot of L choose L over 2, crossing the 10 to the 5th line. That's literally plotting this cliff.
That's literally it. Your code even computes the crossing, the smallest L, where L choose L over 2 exceeds 100,000, and it lands at L equals 20, which it labels the ion Q target, the H02 hardware run. That's the punchline of the whole simulator. Right at L equals 20, the classical brute force dies, and that's exactly the size where you hand the problem to a quantum computer, which represents the state with L qubits instead of L choose N classical numbers. 20 qubits instead of 184,000 amplitudes.
Okay, but hold on. You told me 2 pins ago that sparsity was the loophole. If the matrix is mostly zeros, why can't I just not store the zeros and push way past L equals 20?
You can, and that's regime 2, and it's the honest and important refinement of the wall. Let me draw the distinction sharply, because it changes exactly what's feasible. There are 2 different questions you might ask of the Hamiltonian, and they have wildly different costs. Question 1. Give me all the eigenvalues and all the eigenvectors, the full spectrum. Question 2. Give me just a few eigenvalues, the ones I actually need. Dense ED answers question 1 and pays the full dimension cubed price. But often you only need question 2, and for that, sparsity is your friend.
When would I only need a few eigenvalues?
Constantly in your project. Take the level statistics study, the R ratio, which we're about to get to. To measure the R ratio properly, you want the eigenvalues from the middle of the spectrum, the interior, because the physics of chaos lives in the bulk, not the extreme edges. You don't necessarily need all 184,000 of them. You need a good chunk from the interior. And there's a beautiful trick for grabbing interior eigenvalues cheaply called shift-invert Lanczos.
Break that into its 2 words, Lanczos and shift-invert.
Let's do Lanczos first. Lanczos is a Krylov method, the family of algorithms that never form the whole matrix, they only ever multiply the sparse matrix into a vector. And multiplying a sparse matrix into a vector is cheap. Since each row has only a couple dozen non-zeros, one matrix vector multiply costs roughly dimension times 20 operations, not dimension squared. Lanczos multiplies, gets a new vector, multiplies again, and builds up a tiny ladder of vectors that quickly pins down the extreme eigenvalues. The very highest and very lowest energies, with almost no memory, because you never store the matrix, only the sparse list of non-zeros and a few vectors.
But you just said I want the middle eigenvalues, and plain Lanczos gives me the extremes. So the middle is exactly what it's bad at.
Precisely the problem, and shift-invert is the cure. Here's the idea. Pick a target energy sigma somewhere in the interior, say right in the middle of the spectrum. Now, instead of the matrix H, consider the matrix 1 over the quantity H minus sigma, the inverse of H shifted by sigma. Think about what that transformation does to the eigenvalues. An eigenvalue of H that's very close to sigma, an interior energy near your target, becomes, after subtracting sigma and inverting, a very large number. And an eigenvalue far from sigma becomes small. So the interior eigenvalues you wanted, the ones near sigma, get mapped to the extremes of the transformed matrix, and now plain Lanczos, which is great at extremes, snaps them right up.
Oh, that's slick. You warp the spectrum so the middle becomes the edge, then use the tool that's good at edges. But doesn't inverting a huge matrix cost the same as diagonalizing it?
The sharpest possible question, and the honest answer is, it costs something, but far less than full dense diagonalization, because you never invert explicitly. You factor the sparse shifted matrix once and then solve against it, and sparse factorizations exploit all those zeros. So you trade diagonalize everything for factor 1 sparse matrix and extract a few hundred interior eigenvalues, and that buys you several more sites. It doesn't repeal the exponential L choose N still explodes, and eventually even the sparse vectors won't fit, but it pushes the wall out enough to probe the regime, which is exactly why serious ED studies at larger L reach for SIPI's sparse H with a sigma argument. That's the shift-invert Lanczos computation, and it's the tool waiting in the wings for the larger L points your dense NumPy code can't reach.
So to summarize the how, tiny systems, dense A, get everything. Medium systems where you only need interior levels, sparse shift-invert Lanczos. And past all that, around L equals 20 and beyond. Even the clever classical methods run out and you go to quantum hardware.
That's the complete ladder, and you climbed it yourself. One more honest note, because it matters for your specific project. The level statistics, eigenvalues only, is the cheap diagnostic. You can lean on sparse methods and avulsion. But the OTOC, the butterfly effect in your F3 and F4 figures, that needs eigenvectors, not just eigenvalues, and it needs them across the whole spectrum, because the OTOC is a trace over all states. Eigenvectors are much heavier than eigenvalues. You have to store dimension by dimension worth of them. So the OTOC hits the wall earlier and harder than the R ratio does. That asymmetry, cheap eigenvalues, expensive eigenvectors, is exactly why your run E05 does the level statistics map up to L equals 16, but runs the OTOC only at L equals 12.
That detail actually explains a choice in my own code I'd never questioned. Good. Now let me pull us to part 6, the payoff. I have the eigenvalues. What do I do with them? Because in my project, the headline result is this R ratio going from Poisson to GOE, and I want to finally understand what that computation means.
This is my favorite part, because it's where a list of energies turns into a physical statement about black holes and chaos. Let's build it. Once you've diagonalized, you have a long sorted list of energies. E1 less than E2 less than E3, all the way up. Now here's the key insight that goes back to the founders of quantum chaos. The individual energies don't mean much, they depend on all the messy details. But the pattern of spacings between consecutive energies is universal. It knows only one thing about your system, whether it's integrable or chaotic.
Define those two words physically before we do the statistic, because I use them loosely.
Fair, and it's worth 30 seconds. Integrable means the system has lots of hidden conservation laws, extra quantities that stay constant, which makes its motion regular, predictable, non-mixing. Your chain at V equals 0, no interactions, is integrable. Hardcore bosons with no interaction map exactly to free fermions, which have a conserved occupation for every single momentum mode. A whole tower of conservation laws. Chaotic, or ergodic, or thermalizing, or scrambling means those extra conservation laws are gone. The system mixes everything together, forgets its initial conditions, and reaches thermal equilibrium on its own. A black hole, famously, is the fastest scrambler in nature. And your project's whole thesis is that turning on the interaction V is what tips the horizon chain from integrable into chaotic.
And the spacings between energy levels can tell those two apart just from a list of numbers?
Markably, yes, and the mechanism is called level repulsion. In an integrable system, the energy levels are essentially independent. They don't know about each other, so they land like raindrops, randomly, and sometimes two land almost on top of each other, a tiny gap. That's Poisson statistics. In a chaotic system, the levels repel. Quantum mechanically, they avoid each other, so you almost never see two crammed together. The tiny gaps get pushed out. That repulsion is the fingerprint of chaos, and it shows up directly in the spacing distribution.
So how do you turn that into the single number, the R ratio? Because that's what my adjacent gap ratio function computes, and I want to read it correctly.
Let's read your function line by line. It's short, and it's exactly the standard. First, sort the eigenvalues. Then take consecutive gaps. G sub n equals E sub n plus 1 minus E sub n, the distance between each level and the next. Now here's the clever part, the Oganesian-Husserl trick. Instead of looking at the gaps directly, look at the ratio of adjacent gaps. For each n, take R sub n equals the mine of two consecutive gaps over the max of those two consecutive gaps, the smaller gap divided by the larger gap. In your code, that's exactly the line, R equals np dot minimum of g and its shift, over np dot maximum of g and its shift.
Why the ratio of gaps rather than the gaps themselves? What does dividing buy me?
It buys you a huge practical thing. It's automatically unit-free and scale-free. The raw gaps depend on the local density of levels, which varies across the spectrum. Levels are denser in the middle than at the edges. If you used raw gaps, you'd first have to unfold the spectrum, a fiddly normalization. But a ratio of two neighboring gaps cancels the local density automatically. Both gaps live in the same neighborhood, so their scale divides out. It's a clean, parameter-free number between 0 and 1, and then you average R sub n over all the levels to get one number, mean R, per system.
And the two magic values, where do they come from?
They're mathematical constants for the two universal cases, and they're the two benchmarks hard-coded at the top of your QSIM core. For an integrable system with Poisson-level statistics, the gaps are independent, and you can prove the average ratio is about 0.386. That's R Poisson in your code 3863. For a chaotic system in the relevant symmetry class called the Gaussian orthogonal ensemble, GOE, which applies to a system with time reversal symmetry like yours, the levels repel, the tiny ratios are suppressed, and the average climbs to about 0.531. That's R GOE 5307. So the entire diagnostic is compute mean R. If it's near 0.39, your system is integrable. If it's near 0.53, it's chaotic.
And now the actual result of my project snaps into focus. In Sim 10, mean R at V equals 0 comes out near Poisson, and as I crank V up, it climbs toward GOE. That is the statement, interactions turn the black hole into a scrambler.
That is exactly the statement, and now you can see it's not a vibe. It's a rigorous, basis-independent measurement built entirely out of the eigenvalues you diagonalized for. At V equals 0, free fermions, integrable, mean OR near 386. Turn on V, the extra conservation laws shatter, the levels start repelling, and mean R climbs toward 5307. Panel A of your figure is that climb. And there's the second subtler result in panel B, curved versus flat.
Right, the kappa curved versus kappa flat comparison. Remind me what those two functions actually differ in light of everything we've built.
Now you have the vocabulary for it. Remember, the kappas are the off-diagonal hopping amplitudes, one per bond. Kappa flat makes them all equal, a uniform chain, homogeneous space, every bond the same strength. Kappa curved makes them ramp up linearly with distance from the horizon. That's the black hole's curved metric, encoded directly in the bond strengths. The near-horizon bonds are weak, the far bonds are strong. And critically, in your sweep particles, function you energy match them. The flat chain is set to the same mean hopping magnitude as the curved one. So the two systems have identical overall energy scale and identical interaction V. The only difference between them is the spatial profile of the kappas, the curvature.
So it's a controlled experiment, same everything, except one chain is curved and one is flat. And the result?
The result, your project's headline, reproducing figure 6 of the Benamou paper, is that the curved chain reaches GOE faster than the flat one. At the same V, the same N, the curved horizon chain has a higher mean R, closer to chaos. Curvature strengthens ergodicity. The black hole scrambles more than flat space. And in run EO5, you sharpen it into a single number, delta AR, the curved mean R minus the flat mean R, the pure horizon effect with everything else subtracted out. It comes out small but positive, and, the part that makes it a real result rather than a fluke, it grows as the system gets bigger, from L equals 10 up to your L equals 16 wall probe.
And that growth with size is exactly why the wall matters so much for the science, not just the computation. If delta R keeps growing with L, I want to see it at L equals 20, but L equals 20 is past the wall.
You've just articulated the entire strategic logic of the project, and it's genuinely elegant. The open scientific question, does the horizon effect survive and keep growing toward the thermodynamic limit, lives at exactly the system size where classical diagonalization dies. That's not a coincidence you engineered, it's the natural frontier. The classically accessible sizes show a positive growing effect. Settling it requires L around 20 and beyond. And that's precisely the regime you hand to the IonQ hardware. The wall isn't just a computational annoyance, It's the reason the quantum simulator has a job.
Let me also close the loop on eigenvectors, because we said the R ratio only uses eigenvalues, but the project uses eigenvectors too. Where?
2 places, both about dynamics rather than just the energy spectrum, and now you have the machinery to see them clearly. First, the OTOC, the out-of-time order correlator, your butterfly effect measurement. Look at your OTOC function. The first thing it does is to get eigenvalues and eigenvectors. Then it rotates the operators into the energy eigenbasis and evolves them with those e to the iet phases. Exactly the time evolution recipe from part 4. The OTOC measures how a disturbance on one site spreads to a distant site over time, the quantum butterfly effect, and its speed is the butterfly velocity in your F3 light cone plots. It needs eigenvectors because it's tracking actual operators evolving in time, not just static energies.
And the second place?
The entanglement entropy growth, your F4. You start the chain in a simple Néel state, particles on every other site, which is very far from equilibrium, and you watch entanglement build up as the system thermalizes, computing that needs the full evolved wave function at each time. Eigenvectors again, the U times phased coefficients recipe, followed by a singular value decomposition across a spatial cut. The entanglement racing up to a volume law plateau is the real space signature of the same scrambling that the R ratio sees in the spectrum. 3 independent diagnostics, level statistics, OTOC, entanglement, all built on the one act of diagonalization, all telling the same story. The interacting horizon is a fast scrambler.
That's a genuinely satisfying convergence. Let me try to say the whole arc back to you in my own words, and you catch anything I've bent. A Hamiltonian is the energy operator, which, because states are vectors, becomes a matrix. Its eigenvalues are the allowed energies, and its eigenvectors are the stationary states.
Perfect so far.
We build our matrix by first enumerating the basis, every way to place n hardcore bosons on L sites, which is L choose n configurations, and that number explodes exponentially. Each configuration is a row and column. The interaction term VNN is diagonal. It just counts touching pairs of particles and charges V each. The hopping term, the XX plus YY over 2 with the kappas, is off-diagonal. It connects each configuration to the ones you reach by sliding one particle across a bond, with amplitude kappa for that bond. The matrix is symmetric because energy is real, and it's sparse because each configuration only reaches a handful of others.
Word perfect. Keep going.
Diagonalizing means finding the change of basis, the rotation U that turns off all those off-diagonal kappas and leaves only the energies on the diagonal. It's worth doing above all because of time evolution. The evolution operator e to the minus iht is a nightmare for a tangled matrix but trivial for a diagonal one. Each eigenstate just picks up its own phase, e to the minus iet. So diagonalize once, then evolve to any time for free.
Exactly, and that's the sentence I most want you to keep.
On the computer, small systems get dense exact diagonalization, numpy 8, but memory grows as dimension squared and compute as dimension cubed. So we hit a wall near L equals 20, dimension 184,000, hundreds of gigabytes. Sparsity is the loophole. Krylov methods like Lanczos only ever multiply the sparse matrix into vectors, and shift-invert warps the interior eigenvalues we want into the extremes that Lanczos grabs easily, buying us a few more sites. And eigenvectors are heavier than eigenvalues, so the OTOC hits the wall before the R ratio does.
Build the whole computational picture.
And finally, what we do with it. The eigenvalues give the adjacent gap ratio R, the min over max of consecutive gaps averaged, which is near 0.39 for integrable Poisson and 0.53 for chaotic GOE. Turning on the interaction drives our horizon chain from Poisson toward GOE. Interactions make the black hole scramble, and the curved chain gets there faster than the energy-matched flat one, the horizon effect, which grows with size right up to the classical wall, which is exactly why the frontier lives on quantum hardware. The eigenvectors then feed the OTOC and the entanglement growth, two more views of the same scrambling.
I have essentially nothing to add, which is the goal. You walked in able to run the code, and you're walking out able to derive why every line of it is there. Let me leave you with one framing to carry. Everything we did today, the whole hour, is really one idea wearing three costumes. Constructing the Hamiltonian is writing down how configurations connect. Diagonal for staying put, off-diagonal for moving. Diagonalizing is finding the frame where those connections untangle into pure energies. And solving the physics, chaos, scrambling, black hole dynamics, is reading the pattern in those energies and letting the eigenvectors carry the state through time. Construct, diagonalize, read. That's the whole machine.
Construct, diagonalize, read. One more thing before we close, because you planted it early and I want it explicit. You said the single particle Hamiltonian and the many-body one are different sizes. Just nail that distinction for me, because my code has both chain hopping and hardcore H.
Good catch. Let's not leave it dangling. Chain hopping builds an L by L matrix. That's the single particle Hamiltonian, one particle moving on L sites. So the configurations are just which site is the one particle on. And there are L of them. That's the lattice itself, and it's what you use for the single particle black hole spectroscopy, the Hawking temperature stuff, the TAN profiles. Hardcore H builds the many-body matrix in the L-choose-N space, many particles at once, where a configuration is a whole pattern of occupancies. The single particle problem is cheap and stays cheap. The many-body problem is the one that explodes and hits the wall. The interaction V only exists in the many-body world. One particle can't interact with itself. So the moment you turn on V, you're committed to the big L-choose-N matrix. And that's the whole reason the interacting regime is the hard quantum hardware regime, while the free single particle regime is easy.
That's the cleanest that's ever been for me. Single particle, L by L, easy, the lattice. Many-body, L-choose-N, explosive, the physics. And V lives only in the second.
That's it exactly. And notice it ties the whole episode's tension together. The interesting physics, interactions, scrambling, the black hole as fast scrambler thesis is inseparable from the exponential cost. If it were cheap, you wouldn't need the quantum computer. The difficulty and the interest are the same fact.
George, this genuinely dissolved the fog. I came in able to say the R ratio went from Poisson to GOE like a magic incantation, and I'm leaving able to say Y from the matrix up.
That was the whole aim. Turn the incantation into an understanding. And here's my parting suggestion. Go open Hardcore H right now, take 4 sites and 2 particles, and print the 6x6 matrix. Check it against the one we built by hand, the V's on the diagonal for states 0, 1, 1, 2, and 2, 3, the kappas off-diagonal connecting the configurations that differ by one hop. When your code's matrix matches the one in your head, element for element, you'll never see it as a black box again.
That's exactly what I'm going to do the second we stop recording. Thank you, George. Construct, diagonalize, read.
Anytime, Alice. Now go make that matrix print.